Hey everyone, these are the notes for Chapter 2. I meant to have these out a little bit earlier, but some stuff got in the way and some technical difficulties led me to making them now. Either way, this chapter is from a different textbook than the one we use for the rest of the course. There's a link to it as well. It's the one that's not called Math for Liberal Arts. I don't remember what it is offhand. I think it's like elementary algebra or something like that. But this chapter is specifically from the sections 2.1 to 2.4 in that book, but we're only taking some of that material. If you find that the homework problems are something within your wheelhouse already, you don't have to worry that the rest of that chapter 2.1 to 2.4 will be on the quiz or the test. It's not. Everything you see in the homework is representative of everything you'll see on the test. If you only want to go over particular sections, such as the word problems, or perhaps you want to talk about solving a linear equation or something like that, I've color-coded these slides so that it's easy to distinguish which section we're in. So, without further ado, let's get started. So the first thing we're going to address is using variables. You've probably seen variables in some aspect of your life, but we often use this in math to solve problems. So we can talk about a number like x, where we say something like x plus 12, and that just means we have some number, we've nicknamed it x, and we don't necessarily know what that is. And we can talk about still adding 12 to it, even if we don't know what it is. If we do find out what x is, then we can then replace instances of that with the value we get. So if I say in our x plus 12 example, if I later tell you that x is 73 in that example, then you can replace the x plus 12 with 73 plus 12, which, if you do the addition, should be 85. So we can also talk about something called an equation, which is where you have an equal sign involved. So we'll have an equation. It looks a little complicated, but it's not that bad. It's 5w plus 1 over 3 plus w equals 3w minus 1. Now, because of the equal sign, we actually have implied that w is actually a specific number, one that this is true. Like if we plug in a random number, like if w was 0, for instance, then it would claim that 1/3 plus 0 equals -1, which isn't true. That's just not true. So w definitely isn't 0. It's also not 1, because in that case we'd have 3 equals 2, which is not true. Instead, if I replace the letter w with the number 4, then when you plug it in, you get 5 times 4 plus 1, which is 21, over 3. So 21 over 3 is 7. So 7 plus 4 equals 3 times 4 minus 1, and you get 11 on both sides. This is a solution to this problem. All we're doing is we're checking is 4 if we replace every instance of the letter w with the number 4. We're just checking, is that going to be a valid statement? In this case, we'd end up with 11 equals 11, which we should know is true. So we know it's a solution. And in this case, it's the only solution. There's no other value that you could plug in for w and get a valid answer. When talking about verifying a solution, one of the things to keep in mind is that not every equation has a solution at all. 3x plus 12 equals 3x minus 1 doesn't have a solution. There's no value you can plug in for x and get an answer that's true. Some equations have multiple solutions. The equation x squared minus 100 equals 0 actually has 2. If x is 10, that works. And if x is negative 10, it also works. X to the 5th equals 4x to the 3rd actually has 3 solutions. X can be 2, -2 or 0. You're not expected to solve these. I'm not asking you to. The thing to keep in mind, though, is just that that one solution isn't necessarily the only way. And then you can talk about an equation like 5x minus 2 equals 5x minus 2. I know that that's kind of a silly equation, but because of the way it is, it actually has an infinite number of solutions. You can literally put any value you want for x, and that statement is true. Ooh. Hopefully that's not too hard to see. The other thing that you should be aware of is that we're not limited to a single variable and can often choose to use more than one. So something like 2t minus 7 equals 6y plus 3. Well, if t equals 0 and y equals 3, then it turns out that after some basic arithmetic you can see here, we will get 3 equals 3. And we know that that's true, so we know that the input we gave, which was t equals 5, y equals 0, is a solution. It's not the only solution. In fact, this has an infinite number of solutions as well. You don't need to know what they are, but they're there. And there's no limit to the number of variables that you can use. We could have done this with 15 variables, though it does get messy when you start having that many symbols. So rather than just verifying a solution, what if we instead try to immediately get all of the answers as best we can? So we can consider the equation 6x minus 2 equals 3. Now, we can't just check every value of x, because that would literally take forever, because there's an infinite number of numbers. But we actually know something. Since both sides are supposed to be the same, we know that if we do something to both sides, then that's still true. Like 6x minus 2 is supposed to be 3. So if I subtract 1 from 6x minus 2, then I know that it would be the same as if I subtracted 1 from 3, which would mean that 6x minus 3 is actually the value 2. If we take advantage of this trick, then we can figure out what x is without literally checking everything. So in this case, we have 6x minus 2 equals 3. If I was to add 2 on both sides, then notice that's what it looks like. Then these things collapse with a little bit of simplification, because -2 plus 2 is 0, and 3 plus 2 is 5. We'll end up getting 6x equals 5. If I then divide both sides by 6, then I know that x equals 5/6, which is pretty convenient. And now that's the only possible solution. It doesn't necessarily mean we should check, and we should then verify this by simply plugging in 5/6 into the original equation like we were doing before, and we get 6 times 5/6 minus 2 is equal to 3, and that does simplify into 3 equals 3, so we know we did good. Now, the previous equation we wrote is actually known as a linear equation, which means that the variables we're talking about aren't in a denominator and they're not being taken to some power. So if you take something like x, that's okay, but something like x squared or x cubed is definitely not okay. In addition, this also means that we're not talking about something like a square root or a cubed root or x in an exponent or anything like that. It's just going to be stuff like 7x or x by itself, or the equivalent thing with just a different letter. Linear equations usually have one solution. If both sides happen to be the exact same, that's not true. But, you know, that's good to know. And when solving these, our goal is, just like we did in the last example, we should try to separate the variable stuff onto one side and the number stuff onto the other, and then we basically end up with a solution. And that's how we solve all of these. So consider the first tactic we have is something called combining like terms, which says that if we have adding or subtracting of two numbers, then we can just do the adding or subtracting if we know what the answer is. And that works for both adding and subtracting. So, for example, if we take the equation 2 plus 7 equals 6y minus 2y, well, 2 plus 7, if we use our calculators, we can know that that's a 9. You don't have to use a calculator, but you can. And then 6y minus 2y, well, even though we don't really know what y is, it's still not that crazy to believe that 6y minus 2y is 4y. We can do that same trick if they are both the same variable. That's why they have to be like terms. They have to look the same. We can also add or subtract a value from both sides. We did that before. So if one side of the equation involves adding a value, we can subtract that value from both sides, and we can do a similar thing with subtractions. You can always add or subtract a value from both sides, but we do it usually to kind of undo something. So if we talk about x minus 2 equals 8, I want to get rid of that minus 2, so I'll add 2 to both sides, which will leave us with x minus 2 plus 2 equals 8 plus 2. And the whole point is that when we simplify that, the minus 2 plus 2 thing cancels, and we're left with 8 plus 2, which is 10, so that's x equals 10. We can do the same thing with something like subtraction, where we'll have 7 plus 4x equals 9x. We can subtract the 4x from both sides. And again, we're doing this not because I just think that subtracting 4x is cool, but because subtracting 4x will mean that the 4x term will go away on the left side, leaving it to just be a number, which is our goal. And so in this case, we'd get 7 plus 4x minus 4x equals 9x minus 4x, which simplifies to 7 equals 5x. We can also multiply or divide on both sides. So we do the same thing. We're multiplying by a number. We can divide by that number. And we can do the same thing. If we're dividing by a number, we can multiply by that number to kind of undo it. So we can talk about something like 2x equals 6. We can divide both sides by 2, which just gets us x equals 3, because 6 over 2 is, well, 3, and 2x over 2 is x. And on the opposite side of the coin, if we have r over 3 equals 12, we can actually multiply both sides by 3, which will leave us with r equals 36. When we use this last trick, I really, really recommend that you avoid instances of addition or subtraction in the equation. You don't have to, there's nothing requiring it, but it's really easy to mess up if you don't distribute the multiplication slash division properly. And so it's best to avoid it. So something like 2r equals 25, or 63 equals 3z, or m over 3 equals 35. It doesn't have to look like super nice numbers. It just has to be so there's no addition or subtraction. Then you know you're not going to easily mess something up. It happens to the best of us. Let's pick a harder example. Something like 7x plus 12 equals 9x minus 23. In this case, 7x plus 12 equals 9x minus 23. We need to separate the numbers from the variables. So to do that, we've got a way of, we can either subtract 12 from both sides or add 23 to both sides. And doing either of those things will result on the standalone numbers only being on one side of the equation. And then we can put the variables onto the other one. In this case, I'm going to add 23 to both sides, but there's nothing that says that you have to pick this option. You're perfectly allowed to subtract 12 from both sides, and you'll end up getting the same answer. So if we do that, we'll get 7x plus 35 equals 9x. Remember, the minus 23 and the plus 23 cancel, and 12 plus 23 is 35. So now we need to get those variables on the right side. And we want them on the right side because that's the opposite of where we've just seen this 35 here. So to do that, we're going to subtract 7x from both sides. So if you see, I've subtracted 7x from both sides. And now these 7x's on the left side cancel, even though there's a 35 between them. And we're left with 35 equals 2x. And now we're in that point in the previous bit where we should do our division because there's no addition or subtraction in this operation, so we know we aren't going to make a issue with the distribution of stuff. And doing the division will get us x equals 35 over 2. I heavily recommend that you either put this into a calculator to get a decimal value or leave it as this improper fraction. In math, we often really, really hate the concept of mixed numbers, and as such, we leave it even though it seems a little bit weirder in this format. So let's talk about word problems. We can talk about something like x plus 5. And I mentioned before that if we later find out that x is an actual value, specifically in this case 4, then we can use this to say that x plus 5 evaluates to 4 plus 5, which we know to be 9. That's true even if I was to phrase the exact same problem with words. So I can say Billy has 5 more apples than Alice. Alice has 4 apples, and we can use this exact information. So in this case, Billy's apple count is Alice's apple count plus 5, which is similar to x plus 5. And Alice's apple count is just 4. So, using some basic logic, we know that Billy has 4 plus 5 apples, which is 9. Same exact problem. So let's pick something slightly more complicated. Billy has 3 more speeding tickets than Alice, and Alice and Billy have a total of 17 speeding tickets. Writing this out, we now have a slightly different kind of problem. So now we have Billy's tickets are 3 plus Alice's tickets, and Alice's tickets plus Billy's tickets is 17, because, their total speeding tickets is 17. In this case, we can't just say, oh, we can just do a replacement with 4 or whatever. And we actually have to use the same kind of idea of substitution to solve. But now we're not substituting a number, we're substituting something slightly more complicated. So we know that Billy's tickets is the same thing as 3 plus Alice's tickets. That's the first equation we have. And so since that's true, anytime we see the inserted thing of Billy's tickets, we can replace that with 3 plus Alice's tickets. So, because if we do this in the top equation, it does nothing. So we're going to do it in the bottom equation, which means that we'll do it and say that Alice's tickets plus 3 plus Alice's tickets is the same as 17. We just replaced Billy's tickets with 3 plus Alice's tickets. We can use the tricks from before and solve, and now we know that Alice's tickets is equal to 7. Which means that since Alice's tickets is equal to 7, we can actually put that into the equations now. And we can find that Billy's tickets is 3 plus 7, which we know to be 10. So in the end, we know how many tickets that Billy has and Alice has. We needed both equations to do so, but now we have that information. So we're going to do one last word problem. I know this seems like we're going fast, but there's honestly not a lot of material in this particular chapter. So we're going to say our hardest one yet. We'll say, after searching for a new car, Taylor finds that there's 4 times as many blue cars on the lot as red cars. And after counting, there's actually 75 cars on the lot that are either red or blue. Because I don't want to make this problem really annoying, none of the cars are going to be both colors. So the question is, how many blue cars are there? So when you're doing a problem like this, it's important to use this to scratch off the relevant information, like the things that you don't care about. I don't care about this. I don't care about this. So we really, if you see, the thing we have is we know that there are 4 times as many blue cars on the lot as there are red cars. So this is, let me get this highlighter thing. 4 times as many blue cars. See, that's what that means. And there are 75 cars on the lot in total. So I'm going to pick a different color, pick green. And we know that this is here. Hopefully that's easy to see. But we know that 4 times the red cars equals the blue cars. Well, since that's true, anytime we see blue cars, we can replace it with 4 times red cars. And once again, if we plug it into the first equation, we'll get nothing. And if we plug it into the second equation, we'll get red cars plus 4 times red cars equals 75. Then, using our solving techniques from before, we can get that 5 times red cars equals 75. And then divide both sides by 5, and we get red cars equal 15. Then we can replace red cars into the first equation. And the first equation says that 4 times red cars equals blue cars, so we'll get 4 times 15 equals blue cars, or 60 equals blue cars. So there are 60 blue cars. That's it. So we're done. Heads up that the homework and the quiz are actually due on February 7th. The test is on February 8th. And if you have questions, please contact me on Canvas or email me. And I'm also available during my office hours. If any of this seems really difficult and it feels like you missed something from a previous class or even this one, don't hesitate to ask me. Once again, there are no stupid questions. I will be happy to answer any math questions you have. As I like to say, it is literally my job. Have a great day.